Hi, my name is Lowell Matthews, and today I'll be talking to you about our new simulator, MosaicSim, which is a lightweight modular simulator for heterogeneous systems. We're in a golden age of computer architecture, with exciting new work across the compute stack. But we've been forced into this age by microprocessor trends that have taken place over the last few decades. This graph shows performance markers in log scale over the past 42 years. While transistor and logical core counts have continued to accelerate, single-threaded performance and frequency have stalled, and we seem to have hit a power wall. In their Turing Award lecture in 2019, John Hennessy and David Patterson called on us to employ vertically integrated design that involved applications, domain-specific languages, compiler technology, computer organization, and device technology, all in one unified approach. So what are the implications of this new age for system design and exploration? If we're going to be collapsing the compute stack, this will mean less modularity and more design complexity. Specialized hardware will lead to more components and different components, which further increases complexity. We can expect system design will likely be costlier, more complex, more time-consuming. Simulators provide fast, cheap, and flexible early-stage exploration, and they will be even more important in this era. Unfortunately, current simulator infrastructure have limitations that don't make them well suited for these challenges. Their level of detail is not properly tuned for emerging applications. Some of them skew too far into modeling core microarchitectural detail, while others may not be robust enough to capture application trends and bottlenecks. Current simulator infrastructures don't allow smooth integration of heterogeneous components that may be running at different clock speeds or using different ISAs. They also don't provide the flexibility that we need for agile exploration of programming models, communication paradigms, compiler techniques, and their interactions with underlying hardware. To solve these problems, we introduced MosaicSim. MosaicSim is a heterogeneous system simulator that's designed for hardware-software co-design exploration. MosaicSim is tightly integrated with the LLVM framework, which makes it ISA agnostic and allows it to support specialized instructions. It also allows for flexible programming models and compiler techniques. MosaicSim is designed to allow modular integration of different heterogeneous hardware tiles and communication structures, and all of this with robust timing and energy models. So far I've motivated why we designed MosaicSim. Now I'm going to describe how it works. At a high level, MosaicSim simulates the interactions of multiple heterogeneous tiles that could be out-of-order cores, in-order cores, or accelerators. These tiles are coordinated by a special module called the interleaver, which is responsible for supporting multiple clock frequencies and forcing each of the tiles to take whatever units of work that corresponds to their respective clock frequencies. The interleaver also supports communication across tiles using a special API. MosaicSim comes with a special memory system that includes a multi-level cache hierarchy and a lightweight simple DRAM model. The simple DRAM model captures the effect of latency and bandwidth constraints, but doesn't model the finer microarchitectural details that many applications might not be quite sensitive to. MosaicSim comes with an LLVM-based front end that supports custom programming models, APIs, and compiler techniques. MosaicSim comes with a default abstract tile model. The purpose of this tile model is to perform pre-RTL analysis on kernels to determine if they would benefit from being pinned on a fixed function accelerator. The abstract tile can also be used for general-purpose core simulation. The tile model performs timing simulation, not functional simulation. It directly executes LLVM IR with configurable minimum cycles per instruction type. In order to enforce dependencies between instructions, we use the static data dependency graph provided by LLVM For dynamic dependencies, such as control flow and memory access dependencies, we execute the program on the host machine to generate dynamic traces, which are then used during simulation. An instruction can execute only if all of its dependencies have been resolved. The dynamic traces we collect allow us to perform efficient speculation modeling, since we have perfect knowledge of memory accesses and control flow. So how do we start from an application and execute it on the abstract tile? MosaicSim's LLVM-based front end compiles the application to LLVM IR that is instrumented with special instructions required by the user's programming model or for generating the required dynamic traces. The instrumented program is executed on a host machine to generate control flow and memory access traces. The traces, LLVM IR, and the static data dependency graph are passed to the core model. Each basic block generates one or more dynamic basic blocks, corresponding to the loop iterations. The core model determines each dynamic basic block's memory accesses and control flow paths from the trace generated from the program's execution on the host machine. The abstract tile model provides the opportunity to configure microarchitectural knobs, like the number of functional units and issue width. It also allows the user to configure accelerator-relevant knobs, such as the number of in-flight dynamic basic blocks, which can be used to explore the effect of provisioning hardware resources for parallel execution of loops. In addition to the default abstract tile, MosaicSim also provides the ability to model custom RTL-based accelerators. MosaicSim uses Columbia's open source ESP high-level synthesis tool to generate custom tile models from source code. I'll describe the high-level flow below. The kernel source code is passed through the ESP flow, which provides accelerator templates that are augmented with communication and automatic pipelining for efficient execution. These templates are then instrumented with performance counting code that estimates cycles based on the dimension of arguments. Finally, MosaicSim's API is wrapped around the templates to produce the custom accelerator tile, which effectively becomes a closed-form performance model. From the application side, the source code can be augmented with accelerator invocation API calls and pragmas based on the user's programming models. It is then passed through MosaicSim's LLVM front end, which inserts special instructions and generates dynamic arguments for accelerator invocations. During simulation, when the accelerator invocation instructions are countered, the dimensions are extracted from the trace file, which is then sent to the custom accelerator tile for performance modeling. There's a trade-off between cycle accuracy with physical hardware and the ability to simulate cross-stack effects on heterogeneous systems. In designing MosaicSim, we made the decision to execute LLVM IR directly, with the hope that surrendering cycle accuracy allows us to more effectively model emerging applications and systems. So our performance goals for MosaicSim are to have cycle accuracy that is good enough to determine application trends, determine bottlenecks, and evaluate design points in an agile way. So we conducted some experiments to determine if our general purpose core and memory models provided sufficient accuracy for our goals. We compared our abstract tile-based system to an Intel Xeon core matching its configurations. We then ran benchmarks from Parboil suite on both systems to study the runtime accuracy, scaling with threads, and then we validated MosaicSim's application characterization. Here are results for runtime accuracy. This graph shows runtime accuracy on the y-axis in comparison to that run on x86. Here, runtime accuracy is measured as simulated cycles divided by real cycles. As expected, there's a wide variation in the runtime accuracy across applications because there's no one-to-one mapping between LLVM-IR and x86 ISA. However, with a geomean of 1.099x of a possible best of 1, there seems to be a trend accuracy that is sufficient for heterogeneous system design exploration. And we highlight that in our application characterization. There's a graph of the instructions per cycle of the parabola applications ranked by their memory and compute boundedness. Low IPC applications are expected to be memory bound and high IPC applications compute bound. Breadth first search is often used as an exemplar for memory bound applications, and as expected, it is to the left. Dense matrix-matrix multiplication is towards the right as a well-known compute bound application. In general, the application ordering here largely matches what we see in the literature. Next, we compare scaling trends. So to evaluate how well MosaicSim captures the scaling trends, we compare the speedups from increasing thread and core counts in MosaicSim to those on Intel Xeon Core. We focus on memory-bound applications, compute-bound applications, and memory latency-bound applications here. We find that the scaling trends match quite closely between both systems. However, there's a slight deviation for breadth first search. We attribute this disparity to the fact that BFS heavily utilizes atomic read modify write instructions. The implementation in MosaicSim was not modeled to accurately match that in x86. We also evaluate the accuracy of the RTL-based custom tiles. These tiles were built with the ESP flow that was described previously. We designed accelerator tiles for matrix multiplication, saturating histogram, and element-wise arithmetic. We compared the MosaicSim's platform to FPGA emulation and RTL simulation. Here's a graph of execution time accuracy on the y-axis. We find that MosaicSim had between 97% and 99% execution time match with RTL simulation, and 89% to 93% match with FPGA simulation. So how does MosaicSim compare in speed to other simulators? Measuring speed as millions of instructions per second, we find we are comparable to the speed of Sniper, which is another lightweight simulator. We're also an order of magnitude faster than the detailed Gem 5 simulator. It's worth noting as well that since MosaicSim's custom accelerators provide closed-form performance modeling and not functional accuracy, they're even faster than FPGA emulation and orders of magnitude faster than RTL simulation. To showcase the ease and flexibility with which MosaicSim enables system design exploration, we discuss multiple case studies in this paper. However, in this talk we will discuss only one of them, which is designing a system for an application with alternating phases. Sinkhorn distances is an algorithm for optimal transportation. It executes in alternating phases of matrix multiplication kernels. One kernel is the memory-bound element-wise sparse dense, and the other is compute-bound general matrix-matrix multiplication. The input data to this application determines the weights of each of the phases. In designing a system for this multi-phase application, we start by focusing on what is ideal for each phase. The memory-bound kernel would benefit from techniques such as run-ahead execution, which can be achieved by using the well-known decoupled access execute architecture. The compute-bound kernel, on the other hand, would benefit from fixed function acceleration. What is an optimal heterogeneous architecture that uses these techniques? We explored multiple heterogeneous design points in MosaicSim and ran experiments to evaluate them. These design points included in-order cores, out-of-order cores, decoupled access execute cores, and accelerator cores. This is a graph of performance normalized to that of a single in-order core, showing data for different weightings of Sinkhorn's phases, including equal parts sparse and dense, a sparse heavy weighting, and a dense heavy weighting. We find that the heterogeneous system with in-order decoupled access executes and an accelerator core performed better than all the other system design points that were less heterogeneous. This case study truly showcases the unique value of MosaicSim for agile modular design space exploration. In our paper, we discuss other use cases, including TensorFlow modeling. In conclusion, MosaicSim is a lightweight simulator for full-stack design space exploration. It is tightly integrated with LLVM, which enables agile exploration of cross-stack interactions between programming models, compiler techniques, and accelerator invocations. MosaicSim supports early-stage pre-RTL accelerator modeling, RTL-based accelerator modeling, in addition to modeling for general-purpose cores. Our experiments and case studies show sufficient accuracy and robustness to facilitate agile system design exploration. Thanks for listening to my talk. I want to point out that MosaicSim is open sourced, so please check it out on GitHub.